There's a star at the center of everything we know, 1,400,000 kilometers wide, burning through 4 million tons of itself every second, anchoring 8 planets in their ancient dance through darkness. For 4.5 billion years, it has been there, constant, inevitable, the foundation of every breath, every raindrop, every blade of grass that has ever existed on this world. And now, in this thought experiment we're exploring together tonight, it simply isn't. The sun has vanished. Not dimmed, not cooled, not collapsed into some remnant of itself. Just gone, as if space had folded around the place where it used to burn, leaving nothing but the black between distant stars. One moment, 150 million kilometers away, there was fusion and fire and the gravitational anchor of our entire planetary system. The next moment, there was void. This isn't a story about how such a thing could happen. The laws of physics we understand make this particular scenario essentially impossible. Stars don't simply blink out of existence, mass doesn't vanish, energy doesn't disappear. But we're not here to discuss the mechanism tonight. We're here to walk through something else entirely, the cascade of consequences, the unfolding timeline, the gradual transformation of our world in the wake of the ultimate absence. What we're about to explore together is both more gradual and more absolute than you might expect. The changes don't happen all at once. There are minutes and hours and days where certain things remain unchanged. There are systems that continue, momentum that persists, heat that lingers in ocean depths and Earth's interior. But there is also an end to warmth, to light, to the gentle equilibrium that has allowed complex life to flourish on this particular rock for so very long. Over the next hours together, we'll move through time slowly, from the first 8 minutes when we wouldn't even know yet, through the first day, the first week, the first month. We'll watch temperatures fall in specific, measured ways. We'll see which things fail first and which endure longer than intuition suggests. We'll find the last warm places, the final refuges, the thin edge of possibility for survival in a cosmos suddenly much colder and darker than it was before. This is a journey through incremental loss and unexpected persistence, through the physics of cooling and freezing and the gradual theft of motion from atoms, through ecosystems collapsing in sequence and rare exceptions that might endure, through human ingenuity tested against the ultimate constraint, and through deep time where even those small exceptions fade into equilibrium with the cold of space itself. There will be no urgency in how we move through this, no rush to get to the darkest moments or the coldest temperatures. We'll let each phase unfold at its own pace, examining what changes and what, for a time, does not. We'll find detail in the gradual, truth in the specific measurements and timelines that science gives us when we ask, what would actually happen? So settle in. Let your thoughts slow to match the pace of what we're about to explore. We have time tonight to move carefully through this scenario, to look at it from different angles, to understand both the immediate and the distant consequences of a sun that is suddenly no longer there. The story is measured in minutes that become hours, hours that become days, days that become seasons and years, and eventually the deep time of geological change. It starts, as so many things do, with light, and with the strange, finite speed at which even light must travel through the void. There is something deeply strange about the speed of light being finite. We experience light as instantaneous. You flip a switch, and the room is bright. You look at the moon, and there it is, reflecting sunlight across the 250,000 miles between. But light is not instant. It moves at exactly 299,792,458 meters per second. Fast beyond human comprehension, but still limited. Still taking time to cross distance. From the sun to Earth, photons take 8 minutes and 20 seconds to complete their journey. They're born in the unimaginable fusion pressure of the sun's core, scatter their way out through the dense layers of the star over thousands of years, and then finally, free in the vacuum of space, make the straight shot to Earth in just over 8 minutes. This means that in our scenario, for 8 minutes and 20 seconds after the sun vanishes, we would see nothing different. The sky would still be blue if it were day where you stood. The sun would appear to shine normally, not because it was shining, but because the light that left its surface 8 minutes earlier was still arriving, still flooding into Earth's atmosphere, still scattering through air, molecules to create the blue we associate with daytime. If it were night where you were, the stars would look the same. Darkness would be darkness, no different than usual. The moon, if visible, would show its reflected sunlight, though that sunlight was already the ghost of something gone. Every photon reaching Earth would be a messenger from the past, from a time before the absence began. And it's not just light. According to Einstein's general relativity, gravity itself propagates at the speed of light. Gravity, in this framework, is not a force reaching instantly across space, but a curvature of space-time itself, and changes in that curvature spread outward as gravitational waves at light speed. When a massive object moves or changes, the adjustment to the gravitational field takes time to reach distant locations. This was confirmed experimentally in 2002 when scientists measured the speed of gravity by observing how Jupiter's gravitational field bent light from a distant quasar. The measurements showed that changes in gravity propagate at a speed between 255 million meters per second and 381 million meters per second, completely consistent with light speed. So, for those same 8 minutes and 20 seconds, Earth would continue in its orbit. Not because the sun was still there, but because the information about its absence had not yet reached us. The curvature of space-time in our vicinity would still reflect the presence of that massive object 150 million kilometers away. We would continue tracing our elliptical path, held in invisible curvature, momentum, and gravity in their usual balance. During these 8 minutes, nothing on Earth would change. Not the temperature, not the weather, not the functioning of a single ecosystem. Photosynthesis would continue in every leaf and blade of grass and microscopic phytoplankton. The oceans would move with their tides, governed by the moon's pull and the sun's added influence, though that influence was already only the memory of gravitational curvature. Weather systems would develop and move according to the heat differentials created by sunlight that was real but came from a source that no longer existed. It would be a strange 8 minutes if you knew they were happening. The ultimate grace period, the last moments of normalcy before the information arrived that everything had changed. But in reality, without knowledge of what had occurred, these would be 8 of the most ordinary minutes in history. People would go about their lives. Birds would sing at dawn. The automated systems of solar panels would continue converting arriving photons into electricity, extracting energy from light that had begun its journey from a star that would be gone before the light completed its travel. You could imagine someone looking up at the sun in those final minutes before darkness, perhaps adjusting sunglasses. Against the glare, perhaps feeling the warmth on skin, entirely unaware that they were experiencing the last moments of something that had been true for longer than humanity, longer than mammals, longer than complex life itself. And then the 8 minutes would end. The last photons from the sun's surface would arrive and scatter into Earth's atmosphere. Behind them would be nothing. No new light following. The gravitational wave carrying information about the sun's absence would wash across Earth's position in space. The curvature that had held us in orbit would flatten, and in that moment, everything would change. Not because of what was happening to Earth itself, but because the largest influence on our motion through space had suddenly ceased to exist. People have asked whether we would notice the gravitational change instantly, or whether there would be some physical sensation as Earth stopped orbiting and began traveling in a straight line. The answer is nothing noticeable at all. Orbit is free fall. We don't feel the sun's gravity any more than astronauts on the International Space Station feel Earth's gravity. Both are in constant free fall, which feels like weightlessness, like nothing at all. The transition from orbital motion to straight line motion wouldn't create any jolt or sensation. One moment we'd be falling around the curve that the sun's mass created in space-time. The next moment we'd be moving forward at our current velocity, but now through flat space. The speed would be the same, approximately 107,000 kilometers per hour, or about 67,000 miles per hour, Earth's orbital velocity. But the curve would be gone. We would become, in that instant, a rogue planet. No longer bound to any star, no longer tracing an ellipse, just moving in whatever direction we happened to be pointed at the moment the sun disappeared, carrying all our oceans and atmosphere and life with us on a journey into the vast spaces between stars. But before we follow Earth on that journey, we need to talk about what would happen in those first moments after the 8-minute mark. Because while the gravitational change would be unnoticeable, the absence of light would be anything but. At 8 minutes and 21 seconds after the sun's disappearance, the last light would cross into Earth's atmosphere. And then there would be no more. If you were experiencing day, the change would not be gradual. The sun would not dim or fade or give any warning. It would be there, bright enough that you couldn't look directly at it without hurting your eyes, and then it would be gone. Just gone. As if someone had switched it off, which in our scenario is effectively what happened, though without any switch or any mechanism, just the abrupt transition from presence to absence. The sky would not immediately go black. Earth's atmosphere would still scatter the last light moving through it for a few more seconds. There would be a brief twilight, blue fading toward darkness faster than any sunset because there would be no continued source of light from below the horizon. Just the final scattering of photons that had already arrived, bouncing between air molecules until they were absorbed or escaped to space. Perhaps 10 seconds of rapidly dimming blue. And then darkness. Complete darkness. The darkness of deep space, of places where no star is close enough to provide anything more than a distant point of light. If you were experiencing night, you might not notice immediately. Night is already dark, but you would notice the moon. If the moon were visible, it would go dark in the same moment. Not gradually, but all at once, because the moon produces no light of its own. It shines by reflecting sunlight. Without sunlight to reflect, it would vanish as quickly as the sun itself, leaving only its dark mass moving invisibly against the stars. The stars would remain. This is important. Earth would not be plunged into absolute darkness. The stars would shine exactly as they always had, entirely unaffected by the sun's absence. The Milky Way would stretch across the sky where it was visible, the same band of ancient light from billions of stars in our galaxy's disk. Planets would disappear, Jupiter and Venus and Mars gone dark like the moon, but stars would persist, and they would actually become more visible than they'd ever been for most of humanity. With no moonlight and no light pollution fighting against the darkness, with skies as dark as the darkest wilderness areas had been before the sun's vanishing, the stars would emerge in full glory. The kind of sky that most humans alive in the 21st century had never seen, a sky so full of stars that the darkness between them seemed like the exception rather than the rule. Ancient sky, true night sky, the way it had looked to every human before the Industrial Revolution, before cities, before we filled the night with artificial light. But it would also be a sky without context. No horizon would be visible. No ground beneath your feet could be seen. If you were outside when darkness fell, you would be surrounded by stars in every direction as your eyes adjusted, but you would have no reference for where you were or which direction you faced. The landscape itself would disappear into perfect blackness. This would be terrifying for most people. Humans navigate by vision. We're deeply uncomfortable in complete darkness. The psychological impact of sudden, total darkness during what had been day would be profound. People would freeze, uncertain of where to move, unable to see their hands in front of their faces. There would be panic in many places. Cities with millions of people suddenly unable to see anything beyond the stars above. Vehicles unable to continue safely, though many would still have headlights for a time, as long as batteries held charge. Streetlights would still be on in many places, at least for a while. Anywhere with electrical power would have light from whatever source had been running. Buildings would glow from their windows. The transition wouldn't be to complete darkness everywhere, just to the darkness of night in places where, seconds before, it had been bright afternoon. But power grids would begin to fail. Not immediately, but soon. Most of Earth's electricity comes from fossil fuels, nuclear power, and hydroelectric dams. These would continue working. But the grid itself is more complicated. Supply and demand need to balance constantly. As everyone suddenly switched on lights, as heating systems kicked in responding to the rapid temperature change. As millions of people tried to figure out what was happening and turned to electronic devices for information, the demand would spike. Grids would strain, circuit breakers would trip, and in many regions power would fail within minutes or hours, not from lack of generation capacity, but from the chaos of sudden, unprecedented load changes. Solar power, obviously, would immediately drop to zero. In regions that relied heavily on solar generation, this alone would create grid instability. But that would be a minor issue compared to everything else beginning to fail in sequence. Temperature would be the most immediate physical change, not immediate in the sense of seconds, but immediate in the sense that it would begin the moment no new sunlight arrived. Earth's surface is heated by the sun. Remove the heating source and the surface begins to cool. The mechanism is thermal radiation. Warm objects radiate heat as infrared light. The warmer they are, the more they radiate. Earth normally exists in a balance. Energy arriving from the sun equals energy radiated away to space. Remove the incoming energy, and there's only the outgoing radiation steadily carrying heat away. But this happens slowly at first. The air has thermal mass. The ground has thermal mass. The oceans have enormous thermal mass. All of this stored heat doesn't vanish instantly. It radiates away according to the temperature and the surface area and the efficiency of radiation, but these are processes that take time. In the first hour after darkness fell, the temperature drop would be noticeable but not severe. Perhaps a degree or two Celsius, depending on where you were. Areas that had been experiencing the warmth of afternoon would cool faster. Places that had been in night already would cool at the same rate they had been cooling, which is why deserts, with their low thermal mass and clear skies, get cold quickly after sunset, even under normal circumstances. By the end of the first day, the average surface temperature would have dropped several degrees. Not freezing yet for most places, but noticeably colder. Cold enough that people would need warmer clothing. Cold enough that heating systems would be running constantly where they still had power. And this would just be the beginning, the first hours of a temperature decline that would continue day after day, week after week, until Earth's surface reached a new equilibrium with the cold of space. But we're getting ahead of ourselves. We need to look at what else would happen in those first hours and days as humanity and every other living thing on the planet tried to understand and respond to the sudden, permanent darkness. While darkness covered the planet and temperatures began their decline, Earth itself was already moving in a new direction. No longer orbiting, no longer bound, just traveling forward through space in a straight line at the same velocity we'd had at the moment the sun vanished. That velocity was approximately 107,000 kilometers per hour, or about 67,000 miles per hour. This is Earth's orbital speed, the speed at which we circle the sun each year. It sounds enormously fast, and it is by human standards. But in the context of space, of the distances between stars, it's actually quite slow. To understand what direction Earth would be heading, you need to picture our orbit. Earth moves in an ellipse around the sun, nearly circular but slightly elongated. At any given moment, we're traveling in a particular direction tangent to that orbit. If the sun suddenly ceased to hold us in that curve, we would continue in whichever direction we were pointed at that moment. Not toward the sun, not away from it, but perpendicular to the line between Earth and where the sun had been. Tangent to our former orbit. Where that direction points depends entirely on when the sun vanished. If it vanished in June, we'd head one direction. If it vanished in December, we'd head another, roughly opposite direction. There's no single answer to where Earth would go because our orbital position changes constantly. But wherever we were pointed, that's where we'd travel, moving through the solar system and eventually out of it entirely at a steady 67,000 miles per hour. The solar system itself is large. Neptune, the outermost major planet, orbits at an average distance of about 4.5 billion kilometers from the Sun. At Earth's speed, it would take approximately 4 years to reach Neptune's orbital distance, though we wouldn't necessarily be heading toward where Neptune was. Space is vast and mostly empty. The planets are like grains of sand scattered across a field. The odds of Earth, traveling in a straight line, coming close to another planet would be very low. We'd most likely pass through the orbital regions of Mars, Jupiter, Saturn, Uranus, and Neptune without coming within millions of kilometers of any of them. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending to about 50 astronomical units, 50 times Earth's former distance from the Sun. We'd cross through this region over the course of about 30 years. Then beyond that, the scattered disk, and eventually the Oort cloud, a theoretical sphere of icy objects extending perhaps a light year or more from the Sun, taking more than 17,000 years to cross at our speed. Eventually, after tens of thousands of years, we would leave the gravitational influence of what had been our solar system entirely. We would become a true rogue planet, wandering interstellar space with no parent star, no orbital period, just a steady drift through the galaxy. But long before we reached those outer regions, life on Earth's surface would have ended. The cold would see to that. Because while Earth was gaining independence, launching itself on this long journey into darkness, the temperature was continuing to fall, degree by degree, hour by hour, day by day. The mathematics of planetary cooling are complex. They depend on thermal mass, on the efficiency of radiation, on atmospheric properties and oceanic heat transport, and the temperature gradient between surface and space. But while the mathematics are complex, the outcome is clear. Earth would cool rapidly by geological standards, slowly by human standards, but inexorably toward equilibrium with the temperature of space itself. Average surface temperature on Earth, before the Sun vanished, was approximately 15 degrees Celsius, or about 59 degrees Fahrenheit. This average hides tremendous variation. Desert middays could exceed 40 degrees Celsius. Polar winters could drop below -40. But averaged over the whole surface, over all seasons and all times of day, 15 degrees Celsius was the number. A comfortable temperature, well above the freezing point of water, warm enough for liquid oceans and temperate climates, and the full diversity of life we're familiar with. Without the Sun, that average would begin to fall immediately. The best models suggest that within 1 week, the average global surface temperature would drop to 0 degrees Celsius, the freezing point of water. 7 days from comfortable to freezing on average. But again, averages hide detail. The atmosphere cools faster than the ground. The ground cools faster than the oceans. Different materials have different thermal masses, different cooling rates. Land surfaces would reach freezing much faster than the 7-day average suggests. Within 2 or 3 days, most land areas would be at or below freezing, especially at night, though there would no longer be a meaningful distinction between night and day. Just continuous darkness and continuous cooling. The oceans would resist cooling more effectively. Water has extremely high thermal mass. It takes a huge amount of energy to raise water's temperature, and conversely, water releases a huge amount of energy as it cools. The top layers of the oceans would cool toward freezing within that first week, but the deep oceans, thousands of meters down, would remain relatively warm for much longer. Heat stored in those vast volumes of water would take months or years to radiate away. Air temperature would drop below 0 Celsius in most places by the 3rd or 4th day. By the end of the first week, daytime, which no longer existed but which we can define as the period when that location would normally experience sunlight, would reach -10 degrees Celsius or lower in many regions. Nighttime, which now stretched continuously, would be colder still. This is cold enough to kill most plants. Not immediately, but within days. Photosynthesis requires liquid water. When the water inside plant cells freezes, ice crystals damage cell walls and membranes. Most plants cannot survive prolonged freezing. Some species have adaptations for cold, producing antifreeze proteins or entering dormancy, but these adaptations work for seasonal cold, for the expectation that warmth will return. Against continuous, deepening cold, they provide only brief delays. Small plants, grasses and flowers and crops would die within the first week. Leaves would freeze and blacken. Stems would become brittle. Underground, roots might survive longer where soil temperature remained above freezing, but without photosynthesis, without the ability to produce energy from sunlight, even surviving roots would eventually exhaust their stored resources. Trees would endure longer. Large trees have enormous mass and huge stores of sugars in their wood and roots. They also have slower metabolisms. Some species of trees could potentially survive for years, perhaps even decades, in a frozen dormancy, living off stored resources. But they would be dormant, not growing, not reproducing, just persisting in a state of suspended animation that would end when those stores finally ran out. Humans would face immediate crisis, but not immediate extinction. We could survive 1 week of cold. We had clothing, buildings, heating systems that ran on stored energy rather than sunlight. Many regions of Earth regularly experience temperatures below 0 Celsius during winter. Humans live in Chudispuroid, Antarctica, where temperatures drop below -40. Cold alone, even severe cold, is survivable with sufficient technology and resources. The real problems would be food and energy. Agriculture depends on photosynthesis. All of our crops, all of our livestock, everything we eat traces back to plants capturing solar energy. With photosynthesis stopped, no new food would be produced. We'd be living entirely on stored food that existed at the moment the sun vanished, plus whatever animals remained alive, which would themselves be eating stored food. Developed nations had food storage, but it was measured in weeks or months, not years. As temperatures dropped below freezing everywhere, fresh food would freeze. This would actually help with preservation. Frozen food keeps indefinitely, but it would also make food harder to access and prepare. Frozen meat requires cooking. Frozen vegetables need to be thawed. These things require energy, heat, and energy would become increasingly scarce. Fossil fuels would still work. Oil, natural gas, coal, all of these would provide heat and power independent of the sun. But extraction and distribution require functioning infrastructure. Refineries need power. Pipelines need power. Tanker trucks need roads they can navigate. As the cold deepened and snow began to fall, which it would continuously, across more and more of the planet, infrastructure would degrade. Supply chains would break. Isolated communities would burn through whatever fuel they had stockpiled and then face the cold with nothing but wood fires, assuming they could find wood that wasn't frozen solid. Nuclear power plants would continue running, at least for a time. They don't depend on weather or sunlight, but they need cooling, and they need staff, and they need maintenance. As the crisis deepened, as society began to fracture under the pressure of permanent darkness and impossible cold, how many nuclear operators would remain at their posts? How many would try to get home to their families? How many plants would be shut down safely, and how many would be abandoned? Hydroelectric dams would face their own problems. Rivers would begin to freeze. Not immediately, because flowing water resists freezing, and rivers carry heat from inland areas toward the oceans. But as temperatures dropped further, as the air above rivers cooled to -20, -30 degrees Celsius, ice would form. First at the edges, then across the surface, then eventually down into the current itself. Dams would ice over. Turbines would stop. The massive amount of electricity humanity derived from flowing water would cease. By the end of the first week, human civilization would be in crisis. Not ended, not yet, but fracturing. Billions of people living in regions that had dropped below freezing with inadequate heat. Supply chains breaking down as transportation became difficult. Communication systems failing as power grids collapsed. Governments trying to coordinate response but facing impossible logistics. And outside, in the natural world, the dying would be well underway. Small mammals, birds, insects, anything that couldn't find shelter and warmth would freeze within days. Larger animals would last longer but would be facing starvation as the plants they depended on died. Predators would have brief abundance, feeding on the dying herbivores. But once those prey animals were gone, the predators would starve too. In the oceans, the situation would be different, but no less dire. Surface waters would cool rapidly. Fish that depended on temperature-sensitive metabolisms would struggle, but the deep oceans were vast and held tremendous heat. Marine life in the depths would be largely unaffected, at least initially. The ocean's surface would begin to freeze by the end of the first week in polar regions, but the majority of the oceans would remain liquid, at least for now. The first week, then, would be a week of rapid change but not yet complete transformation. Earth would still be recognizable, atmosphere still breathable, water still mostly liquid, humans still surviving in many regions. But the trajectory would be clear. Everything was cooling, everything was dying, and there was no mechanism by which it could stop. Photosynthesis is the foundation of complex life on Earth, the process by which plants, algae, and certain bacteria convert light energy into chemical energy stored in sugars. 6 molecules of carbon dioxide plus 6 molecules of water plus light energy yields 1 molecule of glucose plus 6 molecules of oxygen. This reaction, endlessly repeated in chloroplasts and on unimaginable scales across the planet, produces nearly all the food that feeds every animal, every fungus, every decomposer in every ecosystem. Without the sun, photosynthesis would stop immediately. Not because the photosynthetic organisms died immediately, though they would die soon enough, but because photosynthesis requires light. No light, no reaction. Even if a plant remained alive, frozen but not yet dead, it couldn't photosynthesize in darkness. The mechanism simply wouldn't function. This would seem to create an immediate oxygen crisis. After all, photosynthesis produces oxygen as a byproduct. If photosynthesis stops, does oxygen production stop too? Yes, it does. But this is actually one of the few areas where the timeline works in humanity's favor, at least briefly. Earth's atmosphere contains approximately 1,200 quadrillion tons of oxygen. That's 1.2 with 18 zeros after it. An absolutely enormous reservoir built up over billions of years of photosynthetic activity, particularly after cyanobacteria invented oxygenic photosynthesis roughly 2.5 billion years ago. Humans and animals consume oxygen through respiration, combining it with organic compounds to release energy. But even with 7 billion humans, billions of livestock, countless trillions of wild animals, insects, fish, and microorganisms all breathing constantly, the oxygen consumption rate is relatively slow compared to the total reservoir. Estimates vary, but most analyses suggest that if photosynthesis stopped entirely, Earth's oxygen would remain breathable for thousands of years before biological respiration depleted it to levels problematic for complex life. Some estimates extend that timeline to tens of thousands of years. The limiting factor wouldn't be oxygen depletion, but rather the buildup of carbon dioxide, which would happen faster, though still over centuries rather than months. So while photosynthesis stopping was catastrophic for food production, it wasn't an immediate threat to breathing. The atmosphere would remain breathable long after every other crisis had already ended humanity and most other surface life. What photosynthesis stopping did mean was the end of energy input at the base of the food chain. Plants stopped producing new sugars, new starches, new structural compounds. They stopped growing. They stopped making seeds. They became, in effect, a fixed reservoir of stored energy. Everything they contained at the moment photosynthesis stopped was all that would ever exist from them. Small annual plants would exhaust their resources quickly. They were adapted for rapid growth during short growing seasons, converting sunlight into biomass as fast as possible. When frozen, their metabolisms would slow dramatically, but they would still be consuming resources for basic maintenance, trying to keep cellular structures intact. Within days or weeks, they would die, their cells too damaged by freezing, their reserves too depleted. Larger plants, perennials, and trees would enter a dormant state if they could. Many tree species have mechanisms for winter dormancy, shutting down growth and drastically reducing metabolic activity. In this state, they could potentially survive for years on stored reserves, waiting for spring that would never come. Eventually, though, even the most efficient dormancy requires some energy. Cells need maintenance. Roots need minimal respiration. Slowly, silently, the trees would exhaust their reserves and die months or years after the sun vanished. For the food chain, this meant all primary producers were either dead or dying. Herbivores would be next. Anything that ate plants would face starvation within weeks. Livestock would be slaughtered for food, which would provide a brief abundance of meat, but wild herbivores, deer and rabbits, and countless insects would die from cold, starvation, or both. Populations would collapse rapidly. Carnivores would experience a strange temporary boom. For a few weeks, there would be more food than they'd ever had. Dying herbivores everywhere, easy to catch, often already dead from cold. Predators would gorge themselves. But this bounty would be brief. Once the herbivores were gone, carnivores would have nothing to eat. They would turn on each other, the larger eating the smaller, but this would only delay the inevitable. Within a month or two, most large carnivores would starve, scavengers would last longer, carcasses would freeze and be preserved in the extreme cold. A dead deer would remain edible indefinitely at -20 degrees Celsius. Crows and ravens and vultures, anything that could find and access frozen carrion, could potentially feed for months. But even scavengers need energy to stay warm and find food. The cold itself would kill many of them long before the food ran out. In the oceans, the pattern would be similar but delayed. Phytoplankton, the microscopic photosynthetic organisms that form the base of marine food chains, would die as surface waters cooled and darkened. But the ocean is enormous, and life in the ocean is distributed vertically through thousands of meters of depth. Surface die-offs would affect surface-feeding fish and the animals that ate them, but deep ocean ecosystems would be less immediately impacted. The twilight zone of the ocean, 200 to 1,000 meters deep, receives almost no sunlight even under normal circumstances. Life there depends on marine snow, the constant rain of dead material from the surface. That source would slow and stop as surface life died, but the transition would take months. Deep ocean fish, those living in permanent darkness already, would be the last affected by the sun's absence, at least in terms of food supply. But temperature would reach even the deep ocean eventually. Slowly, over years and decades, the cold would penetrate downward. Surface ice would act as insulation, slowing the cooling, but it wouldn't stop it. The entire ocean, from surface to seabed, would eventually cool toward equilibrium with space. But that process would be measured in centuries, not days. For humanity, the end of photosynthesis meant the end of agriculture within days. Greenhouses would stay warmer than the outside for a while, but with no sunlight, plants in greenhouses couldn't photosynthesize any more than plants outside. Artificial lighting could theoretically keep photosynthesis going, but the energy requirements would be enormous. Sufficient lighting for meaningful crop production would require more electricity than most remaining power sources could provide. Small-scale survival gardening under LED lights might be possible in isolated locations with nuclear or geothermal power, but feeding populations would be impossible. Stored food would become the only food. Grain silos, frozen meat, canned vegetables, everything humanity had put aside would need to feed billions of people indefinitely. And it wouldn't be enough. Even developed nations with substantial reserves had only months of food. Developing nations often had far less. Global trade networks had collapsed. Ships couldn't navigate frozen seas. Planes couldn't fly through constant storms, through snow and ice and freezing fog. Within a month, mass starvation would begin in some regions. Within 3 months, it would be widespread. Not everywhere equally, different locations would have different resources and different numbers of people competing for those resources, but the general trend would be clear and irreversible. Humanity had been living on the sun's energy, converted to food through photosynthesis. With that conversion stopped, we were living on savings, and the savings were running out. If any humans were to survive long-term in a sunless world, they would need to go underground. Not metaphorically, but literally. Down into the earth, where the cold of space couldn't reach, where the planet's internal heat still flowed outward from its core. Earth's interior is hot. At the center, the inner core is approximately 5,200 degrees Celsius. The outer core, molten iron surrounding the solid inner core, reaches temperatures of about 4,000 to 5,000 degrees Celsius. The mantle, which surrounds the core and makes up most of Earth's volume, ranges from roughly 1,000 degrees at its coolest to 4,000 degrees where it meets the outer core. This heat comes from two sources. First, residual heat from Earth's formation, when countless collisions of planetesimals released enough energy to melt the entire planet. That heat has been radiating away for 4.5 billion years, but Earth is large and rock is an excellent insulator. Heat flows slowly through solid material. Much of the original formation heat remains trapped in the interior. Second, radioactive decay. Earth's mantle and crust contain significant amounts of radioactive isotopes: uranium-238, uranium-235, thorium-232, and potassium-40. These elements decay slowly, releasing heat as they do. This process has been ongoing since Earth's formation and will continue for billions more years. The combined heat output from radioactive decay is substantial, enough to drive plate tectonics and volcanic activity and to maintain the core's temperature despite continuous heat loss to space. This internal heat creates a temperature gradient. The deeper you go, the hotter it gets. Near the surface, Earth's crust is at whatever temperature the surface heating or cooling imposes. But below the depth where surface temperature changes penetrate, roughly 10 to 20 meters, the temperature begins to rise steadily with depth. This increase is called the geothermal gradient. On average, temperature increases by about 25 to 30 degrees Celsius per kilometer of depth. This is an average. It varies by location. In some places, particularly near tectonic plate boundaries or volcanic hotspots, the gradient is much steeper. In other places, in the stable interior of continents, it's more gradual. But everywhere, without exception, the temperature rises as you descend. This means that even with the surface frozen to negative 100 degrees Celsius or colder, there exists some depth where the temperature is comfortable, where human beings could survive without freezing. The question is, how deep? If the surface is negative 100 degrees and the gradient is 30 degrees per kilometer, you'd need to descend roughly 4 kilometers to reach temperatures around 0 degrees Celsius. Another kilometer deeper would bring you to 25 to 30 degrees, genuinely comfortable. 5 kilometers down, roughly 3 miles, and you'd have warmth sufficient for human habitation. 5 kilometers is deep. The deepest mine on Earth, the Tautona gold mine in South Africa, reaches a depth of nearly 4 kilometers. At that depth, the rock temperature is about 55 degrees Celsius without any cooling systems. With the surface frozen, that mine would be a genuinely warm refuge. But Tautona was built over decades by modern mining, operations with massive resources. Could survivors build something similar? Could humanity, in the chaos after the sun vanished, organize the construction of deep refuges? Probably not on a large scale. Deep mining requires enormous amounts of energy, specialized equipment, ventilation systems, and engineering expertise. In the immediate aftermath, with power grids failing and social order collapsing, the resources needed for major construction projects wouldn't be available. But existing mines could serve as refuges. There are thousands of mines worldwide, ranging from a few hundred meters to several kilometers deep. Many of these would offer some degree of warmth even after the surface froze. Communities could potentially form around these locations, using the mine's depth for warmth and whatever surface-stored resources they could access. Geothermal power plants would be even better refuges. Places like Iceland, where geothermal energy is abundant and easily accessible, would have significant advantages. Iceland already heats 87% of its buildings using geothermal energy. The country sits on the mid-Atlantic ridge, where tectonic plates diverge and mantle heat comes close to the surface. Even with the surface frozen, Iceland's geothermal resources would remain warm, heated from below by processes entirely independent of the sun. Survivors in Iceland could potentially maintain heated shelters indefinitely using geothermal heat. They would need food, which would be the limiting resource, but they could maintain warmth, light from geothermal power plants, and enough electricity to run essential systems. Small-scale hydroponic agriculture under artificial lights powered by geothermal electricity might be possible. Not enough to feed the entire population, but perhaps enough for a small community to survive long-term. Other geothermal hotspots would offer similar advantages. Yellowstone in North America, the geothermal areas of New Zealand, parts of Japan, the Philippines, Indonesia. Anywhere with volcanic activity or accessible hot springs would be a potential refuge. But these locations were scattered, and not all of them had the infrastructure to support long-term habitation. Iceland was unique in having both abundant geothermal resources and modern infrastructure built around utilizing those resources. For the vast majority of humanity, though, surviving underground wouldn't be an option. Most people lived far from deep mines or geothermal areas. Most didn't have the resources to reach those locations, especially with transportation networks collapsed. And even the most optimistic scenarios for underground survival assumed tiny populations. Hundreds of people, perhaps thousands, not millions or billions. The mathematics were unforgiving. Food production without sunlight is possible, but requires enormous energy inputs. Artificial lighting for plants, heating for buildings, life support systems, all of these consume electricity. Even with nuclear or geothermal power, there are limits to how much electricity can be generated and how many people that electricity can support. Estimates for long-term underground survival typically land on populations of a few thousand people maximum, assuming access to either nuclear or geothermal power and sophisticated recycling systems for water and air. These populations would need to be highly organized, disciplined about resource use, and capable of maintaining complex systems indefinitely. They would be living in artificial environments, small pockets of warmth and light, in a frozen, dark world, entirely dependent on technology for survival. And even for these survivors, the question would be, survival for how long? Decades? Centuries? Eventually, even nuclear fuel runs out. Uranium and plutonium are finite resources. Even geothermal energy, while vast, changes over geological timescales. Volcanic systems go dormant. Plate tectonics, driven by Earth's internal heat, might slow as the planet cools. On timescales of millions of years, even Earth's internal heat would eventually be inadequate. But those were problems for distant futures. In the immediate aftermath, the question was simpler. Could anyone survive the first year? Could small groups establish stable refuges, find enough food to last through the initial crisis, and build systems that might sustain them into the uncertain future beyond? The answer was, maybe. In specific locations with specific resources, with luck and skill and ruthless efficiency, small groups might endure. But for the vast majority of the 7 billion people alive when the sun vanished, survival beyond the first few months would be impossible. The cold would be too severe, the darkness too complete, the food too scarce, and the isolation too extreme. By 3 months after the sun's disappearance, Earth's surface would be unrecognizable. The average temperature would have dropped to approximately -40 to -50 degrees Celsius, though with significant variation by location. Coastal areas would be slightly warmer due to heat released from the oceans. Continental interiors would be colder, reaching -60 degrees or lower in some regions. At these temperatures, nearly everything liquid would be frozen. Rivers would be solid ice from bank to bank, surface to bottom. Lakes would be frozen through, with ice thickness increasing daily. Even the oceans would begin their transformation from liquid to solid. Ocean water freezes at about -1.8 degrees Celsius, colder than fresh water due to salt content. But freezing an ocean is more complicated than just reaching that temperature. The ocean is not a uniform body of water. It has currents, temperature gradients, varying salinity at different depths. The surface freezes first because it's in contact with the cold atmosphere. But beneath the surface, water can remain liquid even as ice forms. Above, by 3 months in, the polar oceans would be covered by thick sea ice. These regions already form seasonal ice under normal conditions. With permanent darkness and continuously dropping temperatures, the ice would grow much thicker and would extend far beyond normal polar boundaries. Ice would spread from the poles toward the equator at a rate of several kilometers per day, covering more and more of the ocean's surface. The Mid-Atlantic, the North Pacific, the Southern Ocean surrounding Antarctica, all would be frozen at the surface. Ice thickness would vary, but in polar regions it could already be several meters thick. This ice would be relatively smooth initially, flat frozen seawater, but wind would work it over time, breaking it apart and pushing sheets together, creating pressure ridges and jumbled ice fields similar to Arctic pack ice but on a much larger scale. Closer to the equator, the ocean would resist freezing longer. Equatorial waters are warmer to begin with, and the ocean there is deeper with more thermal mass. But even tropical seas would begin to freeze by the 3-month mark. Perhaps not solidly, perhaps just a thin layer of ice forming overnight and thickening gradually, but the freezing would have begun. Beneath the ice, the ocean would remain liquid for a long time. Ice is an excellent insulator. Once a thick layer forms on the surface, it slows heat transfer from the water below to the air above. The ocean would cool from the top down, very slowly, with the deep ocean retaining heat for years or even centuries. This has important implications for marine life. Surface ecosystems would be destroyed. Anything living in the top 100 meters would die from cold and darkness. But deeper down, conditions would remain relatively stable. The deep ocean is already dark. Life there has never depended on sunlight. Temperature in the deep ocean is normally just a few degrees above freezing, cold but stable. That stability would persist. Deep sea fish, tube worms, crabs, the entire ecosystem around hydrothermal vents, all of this would continue largely unaffected. Hydrothermal vents are powered by Earth's internal heat, not by the sun. Superheated water, 300 to 400 degrees Celsius, jets out of vents on the seafloor carrying dissolved minerals. Bacteria use these minerals for energy through chemosynthesis, converting chemicals into organic compounds. These bacteria support entire food webs: tube worms housing bacteria in specialized organs, shrimp and crabs feeding on bacterial mats, fish feeding on the invertebrates. These ecosystems would be among the only places on Earth where life continued normally. For them, the sun's absence would be irrelevant. They had never seen sunlight, they had never depended on it. The vent chemistry would continue unchanged, the food chains would remain intact. In the absolute darkness of the deep ocean, in water that stayed liquid under kilometers of ice, life would persist. But this would be a tiny fraction of Earth's former biodiversity. A few hundred species in isolated vent fields scattered across the ocean floor. Everything else, everything that had depended on photosynthesis, everything that needed warmth or light or liquid water near the surface would be gone or dying. On land, by 3 months, there would be almost no large animals alive outside of heated refugees. Anything exposed to the cold would be frozen solid. Bodies would be preserved in ice, animals caught mid-stride or curled in final sleep, frozen so quickly that decomposition never began. The surface would be a snapshot of mass death, preserved indefinitely in temperatures far below zero. Snow would be falling constantly in many regions. Not water snow, at least not entirely. As temperatures dropped below the freezing points of atmospheric gases, new kinds of snow would begin to fall. Carbon dioxide snow, dry ice, would begin forming when temperatures dropped, below -78 degrees Celsius. In the coldest regions, this would happen by the 2-month mark. By 3 months, dry ice snow would be falling regularly in continental interiors. This snow would accumulate, layer upon layer, building up, mixing with water ice from earlier when temperatures had been warmer. The result would be a surface that was part water ice, part dry ice, gradually building into a frozen landscape of mixed ices. Wind would still blow, driven by temperature differences between the slightly warmer oceans and the colder continents. But these winds would be different from winds under normal conditions. Colder, denser, carrying ice crystals instead of water vapor. Storms would sweep across frozen seas and buried continents, howling through darkness, creating drifts and dunes of ice that grew and shifted in patterns no human would witness. For any survivors in underground refugees, the surface would be inaccessible and deadly. Emerging would mean instant exposure to -50 degrees or colder. Exposed skin would freeze in minutes. Breathing unheated air would damage lungs. Any equipment would need extreme cold rating, the kind used in Antarctic research stations, and even that might not be sufficient for the deepest cold. Supply runs to the surface would be dangerous and brief. Survivors would need to stay underground, relying entirely on whatever they'd stockpiled and whatever they could produce with geothermal or nuclear power. The surface would be lost to them, a frozen wasteland, hostile to all life. And this was only 3 months in. The cooling would continue. At 1 year after the sun's disappearance, Earth would have cooled to approximately negative 100 degrees Celsius on average. Some regions would be colder, continental interiors reaching negative 120 degrees or lower. Coastal areas warmed slightly by oceanic heat might still be negative 80 to negative 90 degrees. But everywhere, without exception, would be far below the temperature at which any surface life could survive. The oceans would be frozen solid at the surface to depths of several hundred meters. Ice thickness would vary with location, but in polar seas, the ice could be 500 meters thick or more. This ice would not be clear. It would be opaque, white or blue-white, filled with trapped air bubbles and stress fractures. The top surface would be rough, sculpted by wind into patterns of ridges and valleys. Beneath this ice, the deep ocean would remain liquid. Heat from hydrothermal vents, heat from the seafloor itself where Earth's interior contacted the ocean, heat from the sheer thermal mass of billions of tons of water, all of this would keep the depths liquid. Temperatures would be dropping slowly, perhaps a degree or two per year in the deepest parts, but liquid water would persist for centuries yet. On land, the ice would be thicker in some ways, thinner in others. Water ice would dominate in some regions, but in the coldest areas, other substances would be freezing out of the atmosphere. Carbon dioxide snow, which began falling when temperatures dropped below negative 78 degrees, would have accumulated in thick layers. Nitrogen, which makes up 78% of Earth's atmosphere, would begin to condense when temperatures dropped below negative 196 degrees. This hadn't happened yet at 1 year, but it was approaching. The atmosphere itself would be thinning. As temperatures dropped, gases condensed and fell as snow. Carbon dioxide was first, turning from gas to solid and drifting down to accumulate on the surface. This reduced atmospheric pressure slightly. Less gas in the atmosphere meant less air pressure, less wind, less weather in the traditional sense. But there would still be movement, still be transfers of ice and frost driven by temperature differences. Oxygen and nitrogen, the main components of the atmosphere, would remain gaseous at negative 100 degrees, but they would be far denser than normal, cold gases compressed by their own weight. The atmosphere would be shorter, more compressed toward the surface, clear and still, in ways it never had been when warmed by sunlight. For any surviving humans, 1 year would mark a threshold. This was about as long as food stockpiles could reasonably last. Any group that had made it to the 1 year mark would have exhausted most stored food. They would be entirely dependent on whatever they could produce artificially: hydroponic gardens under LED lights, algae cultures in nutrient baths, maybe fish tanks or small-scale protein production. All of this required enormous energy inputs and sophisticated systems maintenance. The groups most likely to survive would be those in geothermal areas with reliable power and those who'd had the longest time to prepare. Iceland's survivors, if there were any, would have the best chance. They had geothermal power, they had infrastructure built around using that power, and they had a small enough population that resources might stretch further. But even ideal groups would be struggling. Psychological stress would be enormous. Living underground in artificial light, never seeing the surface, knowing that Earth had become permanently hostile to human life. Depression would be common. Conflicts over resources and decisions would threaten group cohesion. And any technical failure, any breakdown in life support or power generation or food production would be catastrophic. Optimistically, maybe a few thousand humans would still be alive at the 1 year mark, scattered across perhaps a dozen refuges worldwide. Realistically, it might be fewer, and the long-term outlook would be grim. These survivors would be living on borrowed time, dependent on complex technologies that would eventually fail, consuming resources that couldn't be replaced, postponing the inevitable but unable to prevent it. In the natural world, surface life would be effectively extinct. Any plant still technically alive would be frozen dormant, but most would be dead, their cells ruptured by ice crystals, their tissues damaged beyond recovery. Large trees might have remnants of viable tissue in their heartwood, protected by thick bark and insulated by their own mass, but they would be frozen solid, buried in ice and snow, with no possibility of awakening. Animals would be gone. Anything that hadn't found shelter in the first days and weeks would be frozen, preserved in the ice like mammoths in Siberian permafrost. Birds that had tried to migrate to warmth that no longer existed would have fallen from the sky. Marine mammals would have struggled to find breathing holes as the ocean surface solidified. Land mammals, even those adapted for cold, like polar bears and Arctic foxes, would have found temperatures dropping far beyond their tolerance. The 1-year mark would represent, essentially, the end of the old Earth. The planet of forests and grasslands, of flowing rivers and living seas, of abundant life in every climate zone, that Earth would be gone. What remained would be a frozen ball of ice, silent and dark, orbiting nothing, traveling through space on a trajectory that would never bring warmth again. And yet, not everything would be dead. In the deep ocean, kilometers below the ice, life would persist. After the first year, the changes would slow, but not stop. Temperature would continue to decline, approaching but never quite reaching absolute zero, the coldest possible temperature at negative 273.15 degrees Celsius. Earth's final equilibrium temperature would depend on several factors: residual heat from Earth's interior, heat from tidal forces if Earth still retained the Moon, and the baseline temperature of space itself. Space is not truly at absolute zero. The cosmic microwave background, the afterglow of the Big Bang, permeates all of space with a temperature of approximately negative 270 degrees Celsius, or about 2.7 degrees above absolute zero. This is the temperature that anything in space, isolated from other heat sources, will eventually reach. It's the background temperature of the universe itself. Earth wouldn't cool quite to this temperature because of internal heat. The core's temperature, the mantle's warmth, these would prevent the surface from reaching the cosmic background temperature, but over centuries and millennia, the surface would approach equilibrium with space, moderated only slightly by the slow flow of heat from below. By century 2, the average surface temperature might be negative 150 degrees Celsius. Oxygen would remain gaseous, but just barely. At negative 183 degrees, oxygen begins to condense into liquid. Earth hadn't reached that temperature yet, but it was approaching. By century 5, the coldest regions would have dropped below the condensation point of oxygen. The gas would begin to liquefy, forming puddles and pools of pale blue liquid oxygen on the frozen surface. These would accumulate in low-lying areas, valleys, and basins, gradually increasing in volume as more oxygen condensed from the atmosphere. This would mark a visible change. The atmosphere, which had been mostly nitrogen and oxygen throughout Earth's history, would be separating into its components. Oxygen, with its higher boiling point, would condense first, leaving nitrogen to dominate the thinning atmosphere. Atmospheric pressure would continue to drop, not just from cooling, but from actual loss of volume as gases transition to liquids and solids. By millennium 1, nitrogen itself would begin to condense. At negative 196 degrees Celsius, nitrogen becomes liquid. Earth's surface would be approaching this temperature in many regions. Liquid nitrogen would rain from the sky, a strange cold rain falling onto a landscape already covered in water ice, carbon dioxide snow, and pools of liquid oxygen. Eventually, both nitrogen and oxygen would freeze solid. Nitrogen freezes at negative 210 degrees Celsius. Oxygen freezes at negative 219 degrees. As Earth's surface dropped through these temperatures over thousands of years, the atmosphere would literally fall, condensing and solidifying and accumulating on the surface as layers of frozen gas. This would create a landscape unlike anything that exists naturally elsewhere in the solar system. Earth would be covered in mixed ices: water ice from the original oceans and atmosphere, carbon dioxide ice from early atmospheric condensation, nitrogen ice, and oxygen ice from later cooling. The surface would be layered, different ices at different depths, sorted roughly by their freezing points. Atmospheric pressure at the surface would drop to near vacuum levels. Not complete. Vacuum, some gas would remain, sublimating from the frozen surface, but pressure would be a tiny fraction of what it had been. Perhaps 1%, perhaps less. Walking on this surface, if anyone could walk, would be like walking on the surface of Mars, requiring pressure suits, dealing with the hazards of near vacuum. The ice layers themselves would be dynamic, though slowly so. Temperature variations, even in deep cold, would cause ice to sublime in warmer areas and redeposit in colder areas. Wind, though faint with the thin atmosphere, would still move ice crystals. Over millennia, the surface would evolve, ice flowing like glaciers but much, much slower, dunes forming from frozen nitrogen drifting across frozen water. Earth's tectonic activity would slow as the planet cooled. Plate tectonics depends on heat flow from the interior maintaining the mantle's plasticity. As that heat flow decreased, the mantle would become more rigid, plates would move more slowly, eventually stopping altogether. Earthquakes would become rare, then cease. Volcanism would end. The dynamic Earth, the planet of moving continents and erupting mountains, would become geologically dead. But complete geological death would take billions of years. The heat in Earth's interior, particularly in the core, was substantial. Radioactive decay would continue producing new heat for billions of years. On timescales of millions of years, Earth's surface might cool to -200 degrees Celsius or colder, but the core would remain thousands of degrees hot, and the heat flow from core to surface would persist. This meant that deep beneath the frozen surface, temperatures would remain above freezing. The geothermal gradient would persist, steeper than before because the surface was so much colder but still present. At some depth, perhaps 50 or 100 kilometers down, the temperature would still be warm enough for liquid water, for chemistry, potentially even for life, adapted to those conditions. The mono lake bacteria, discovered in California, can survive in conditions that would kill most organisms. They can tolerate high pH, high salt concentration, and can use arsenic in place of phosphorus. Life is adaptable. The question would be whether any life could access the warmth deep underground, and whether it could persist there over geological timescales without an energy source. Without photosynthesis, without chemical energy from atmospheric processes, the only energy sources would be chemical gradients in the rocks themselves and heat flow from the interior. This was enough to support microbial life. Simple single-celled organisms could potentially persist in fractures and pores in rock hundreds or thousands of meters below the surface, living on chemical reactions and geothermal heat. But this wouldn't be complex life. No animals, no plants, just bacteria and archaea, simple cells scraping out existence in the last warm places. And even these would be in decline as the planet cooled and the energy gradients they depended on weakened. On timescales of tens of millions of years, even deep microbial life would likely fade. The cold would penetrate ever deeper. Energy sources would diminish. Earth would approach true sterility, lifeless from surface to deep interior. A frozen ball of ice and rock carrying the preserved remains of 4 billion years of evolution, but no longer hosting any living process. Except perhaps in one final refuge. The deep ocean would be the last place on Earth to retain liquid water and the last place to support complex life. Even as the surface froze and centuries passed, even as the ice thickened and the atmosphere condensed, the deepest parts of the ocean would remain liquid, warmed from below by Earth's internal heat. The average ocean depth is approximately 3,800 meters. The deepest point, the Challenger Deep in the Mariana Trench, reaches nearly 11,000 meters. These depths would be insulated by kilometers of ice above, ice that would grow thicker over the centuries, but would take an extremely long time to freeze the entire water column. Heat flow from the seafloor would prevent complete freezing. The oceanic crust is thinner than continental crust, and heat from the mantle below reaches the seafloor more easily. In many places, that heat is concentrated in hydrothermal vents, places where seawater seeps down through cracks in the crust, is heated to hundreds of degrees by proximity to magma, and jets back up laden with dissolved minerals. These vents support unique ecosystems. In the total darkness of the deep ocean, where no photosynthesis is possible, life depends instead on chemosynthesis. Bacteria use the chemicals from the vents, particularly hydrogen sulfide, to produce energy. These bacteria form the base of the food chain, supporting tube worms, clams, shrimp, crabs, fish, and a variety of other organisms. These vent communities discovered in 1977 near the Galapagos Islands were a surprise to science. Life thriving in darkness, in extreme heat, in toxic chemicals, entirely independent of the sun. The discovery reshaped understanding of where and how life could exist. It also provided the answer to survival in a sunless world. If life could exist at vents under normal conditions, it could potentially survive even after the surface froze. The vents emit water at temperatures between 200 and 400 degrees Celsius. This water would be above the boiling point at surface pressure, but at deep ocean pressure, several hundred atmospheres, water remains liquid at these temperatures. It's superheated, far hotter than boiling at the surface, but still liquid. This extreme heat would be advantageous in a freezing world. Even as the ocean cooled from above, even as ice thickened and temperature at the seafloor dropped, the vents would remain hot. They would become islands of warmth in an increasingly cold ocean, and life would concentrate around them. Initially, as the ocean cooled, vent organisms would notice little change. The deep ocean is already cold, normally just a few degrees above freezing at depth. Cooling another few degrees would be within the normal variation these organisms experience. But as the ice thickened above and insulated the ocean, the situation would stabilize. The vents would remain hot, the immediate vicinity would remain warm, and life would persist. How long could this last? How long could hydrothermal vent ecosystems survive in a frozen ocean on a frozen planet? The answer depends on how long the vents themselves remain active. Hydrothermal vents are powered by volcanic and tectonic activity. As long as the mantle convects, as long as magma rises beneath mid-ocean ridges and creates new crust, the vents will flow. This process is driven by Earth's internal heat, and that heat will persist for billions of years, far longer than the Sun has left in its main sequence lifetime under normal circumstances. So the vents could potentially remain active for millions of years after the Sun vanished, perhaps tens of millions of years. The exact timeline would depend on how quickly Earth's interior cools, which in turn depends on heat flow and the rate of radioactive decay, but the process would be slow. During this time, vent ecosystems would be the only complex life on Earth. Giant tube worms could grow up to 2 meters long and live for hundreds of years. These creatures, Riftia pachyptila, harbor bacteria in their tissues that provide them with nutrition through chemosynthesis. They have no mouth, no digestive system, relying entirely on their bacterial symbionts. In a frozen ocean, they would continue their lives, growing, reproducing, forming communities around the vent openings, entirely unaware that the rest of the planet had died. Vent shrimp, white blind shrimp that cluster around vents in enormous numbers, would continue feeding on bacterial mats. Yeti crabs, which farm bacteria on their hairy claws, would continue their strange lives. Fish adapted to the deep, with large eyes or no eyes, with pressure-resistant bodies and slow metabolisms, would hunt among the vent communities, the last predators in the last functioning ecosystems. But these communities would be isolated. Normally, vent life is spread across thousands of kilometers of mid-ocean ridges, different vent fields connected by currents that carry larvae and enable genetic exchange. In a frozen ocean, with currents slowed or stopped by ice above, isolation would increase. Each vent field would become its own separate ecosystem, unable to exchange organisms with others, evolving independently. Over thousands of generations, this isolation could lead to speciation. Each vent field might develop its own unique species, adapted to local conditions, diverging from populations at other vents. The process would be similar to island biogeography, where isolated populations on islands evolve differently from mainland populations. The vents would be islands of life in an ocean of darkness and cold, but isolation also increases vulnerability. If a vent field stops flowing, if the local volcanic activity ceases, the entire community would die. There would be no recolonization from other vents. The species unique to that field would go extinct. Slowly, over deep time, vent after vent would go dormant. The communities would shrink. Biodiversity would decline. The last complex life on Earth would be dying, not quickly, but gradually, inevitably, as the power source that sustained them weakened and failed. Eventually, millions of years after the sun vanished, the last vent would cool. The last tube worm would die. The last shrimp would freeze. And Earth would be truly lifeless, an ice ball carrying the frozen remains of what had once been a living world, drifting through the dark between stars. While all of this cooling and freezing and dying was happening, Earth would be traveling. Moving through space at 67,000 miles per hour, heading away from where the sun had been, crossing first the inner solar system, then the outer reaches, then eventually leaving the solar system entirely. That journey would be long. Space is vast, and even 67,000 miles per hour is slow on cosmic scales. To put it in perspective, light travels at 670 million miles per hour. Earth would be traveling at roughly 1/10,000th the speed of light. At this speed, crossing a single light year, the distance light travels in 1 year would take about 10,000 years. The nearest star to what had been our solar system is Proxima Centauri, approximately 4.24 light-years away. At Earth's speed, reaching Proxima Centauri would take about 42,000 years. But Earth wouldn't necessarily be heading toward Proxima Centauri. The direction would depend entirely on where Earth was in its orbit when the sun vanished. We might be heading toward Proxima, or away from it, or in some other direction entirely. More likely, Earth would be heading into the general disk of the Milky Way, or perpendicular to it, depending on the orbital timing. The solar system orbits the center of the Milky Way galaxy once every 225 million years at a speed of about 500,000 miles per hour. Earth, freed from the sun's gravity, would retain the solar system's galactic orbital velocity, but would also have its own orbital velocity from circling the sun. The combination of these velocities would determine Earth's path through the galaxy. That path would be a gentle curve influenced by the Milky Way's gravity. Earth wouldn't escape the galaxy. The galactic gravitational field is far stronger than the sun's had been, and Earth's speed was insufficient for galactic escape. Instead, Earth would become a galactic orbiter, a rogue planet, circling the galactic center on its own elliptical path, not bound to any star, but still bound to the galaxy as a whole. Over millions of years, Earth would pass through different regions of the galaxy. The Milky Way is approximately 100,000 light-years in diameter, containing 200 to 400 billion stars. Space between those stars is vast and mostly empty. The average distance between stars in our region of the galaxy is about 4 light-years. At Earth's speed of 1/10,000th light speed, crossing from one star's vicinity to another would take roughly 40,000 years. During this journey, Earth might pass near other stars. Not close enough to be captured into orbit, that would require slowing down significantly, which wouldn't happen unless Earth somehow collided with a massive cloud of gas or got caught in a complex gravitational interaction with multiple stars. But passing near enough to see the star brighten in the sky to receive faint amounts of starlight to maybe, briefly, warm up by a few degrees from a distant star's radiation. These encounters would be rare. Space is so vast that most of Earth's journey would be through the dark between stars, the deep interstellar medium where the nearest star is just a bright point in the sky and warmth is purely from Earth's interior. Decades would pass, centuries, millennia, with nothing changing except Earth's position relative to distant stars. Rogue planets are not uncommon in the galaxy. Recent studies suggest there might be billions of them, maybe trillions. Planets ejected from their birth systems by gravitational interactions or stellar events, now wandering the galaxy independently. Earth would join this population, one frozen world among many, each carrying its own history, its own story of formation and loss. Some of these rogue planets might have retained atmospheres. Some might be warm enough from internal heat to support subsurface oceans. A few might even have life, organisms adapted to survive without starlight, living in underground environments warmed by radioactive decay or tidal heating from large moons. Earth, in its frozen state, would be among the colder rogues, having lost most of its atmosphere to surface condensation, but it would still retain the story of what it had been. That story would be written in the ice. Layers of frozen ocean containing marine fossils. Frozen forests preserved where they stood. Buildings and cities and roads buried under ice. Artifacts of a technological civilization that briefly flourished and then ended when the sun disappeared. Any alien civilization that discovered Earth millions of years in the future would find a fossil record unparalleled in the galaxy. A complete preservation of an entire biosphere frozen in time. But would anyone ever find it? The odds of another civilization randomly encountering Earth would be vanishingly small. The galaxy is too large, space too vast, and rogue, planets too dark to detect easily. Earth would most likely spend the rest of time as a silent wanderer, traveling through the dark, slowly cooling, eventually becoming just one more cold object among countless billions in the Milky Way's vast expanse. Over billions of years, Earth would continue to cool toward equilibrium with a cosmic microwave background. The ice would remain, undisturbed except by rare collisions with asteroids or comets. The core would eventually solidify as the last heat radiated away. Tectonic activity would cease entirely. Earth would become geologically dead, a frozen relic, still orbiting the galaxy but no longer changing in any meaningful way. And then, roughly 5 billion years from now, if Earth hadn't been destroyed by some collision or captured by some star, the Milky Way would collide with the Andromeda Galaxy. The two galaxies would pass through each other, stars and planets rearranging in new patterns. Earth might be flung into intergalactic space by gravitational interactions, or it might be captured into orbit around some star in Andromeda, possibly warming up again if that star was similar to the Sun. But that would be so far in the future and so dependent on unlikely specific events that it exists only as an abstract possibility. For all practical purposes, Earth's fate after the Sun vanished would be to freeze, to die, and to wander. A monument to what had been, traveling through darkness, forgotten by the universe. There's something quietly absolute about the scenario we've walked through together tonight. Not the drama of it, not the catastrophe, but the simplicity. Remove the source of energy and the cascade follows. Temperature drops, life ends, ice accumulates. The processes are physics, impersonal and inevitable, playing out over hours and days and years according to rules that don't care about meaning or memory. Earth would become a different kind of object. Not a living world, not a planet in the sense we understand that word, but a frozen ball of ice carrying the records of what it had been. Every ocean, every forest, every creature that ever lived, all of it locked in ice, preserved perfectly at temperatures where decay doesn't happen, where nothing changes except the slow cooling toward equilibrium. The last living things would be bacteria around hydrothermal vents, kilometers underwater, beneath ice that would take millennia to freeze through. They would persist the longest, not because they were special, but because they happened to exist in the one environment that remained stable the longest. Eventually, though, even they would end. The vents would cool, the water would freeze, and Earth would be silent. That silence would last. Not years or centuries, but potentially billions of years, interrupted only by the faint crackle of ice shifting, the distant thud of a meteor impact, the gradual creaks and groans of a world continuing to cool. Earth would travel through the galaxy, one rogue planet among billions, indistinguishable from any other except for what was frozen in its ice, if anyone ever bothered to look. We've spent time tonight exploring the timeline, the specific ways this transformation would unfold. 8 minutes of normalcy after the sun vanished. darkness at 8 minutes 20 seconds, freezing within a week, oceans frozen at 3 months, 1 year to surface temperatures of -100 degrees, centuries to atmospheric collapse, millennia to complete equilibrium with the cold of space, each phase following naturally from the one before, each determined by basic physics and the properties of matter at different temperatures. What we've described is unlikely to happen. Stars don't vanish. The sun will continue burning for another 5 billion years, gradually brightening, eventually expanding into a red giant and destroying Earth in a completely different way. But exploring this scenario, walking through what would happen if the heat source disappeared, shows something true about our relationship with the star we orbit. We exist in a thin shell of temperature around a rocky planet, kept warm by fusion happening 93 million miles away. Remove that fusion, and the shell collapses. The comfortable range where water is liquid and chemistry is fast narrows and disappears. We're left with cold and ice and the slow processes of frozen worlds. There's no urgency in this. No need to worry about a sun that won't vanish. But there's value in understanding the system we're part of, the dependencies that make life possible, the narrow ranges of temperature and energy that support complexity. The scenario we've explored is hypothetical, but it illuminates something real about our place in the cosmos. Thank you for walking through this with me tonight. If you found this exploration of the frozen Earth interesting, I hope you'll consider liking this video and subscribing to the channel. We cover these kinds of cosmic scenarios regularly, always grounded in real science, always exploring what the universe teaches us about scale and time and the strange, narrow conditions that allow life to exist at all. There are more scenarios to explore, other thought experiments, other ways of understanding the cosmos by asking what would happen if some fundamental condition changed. If you enjoyed this journey into the dark and cold, there will be more journeys ahead. Different questions, different timelines, but the same approach. Slow, careful, thorough, letting the physics tell the story. Until next time, rest well. The sun is still there, still burning, still providing the energy that keeps our world alive. That's unlikely to change in any of our lifetimes. But now you know, in quiet detail, what would happen if it did.